Welcome to Dr. Boxy Teaches Electromagnetism. In the previous lesson, we looked at the divergence and the curl of the electrostatic field. The divergence of the electrostatic field gave us something known as Gauss's law, and we looked at some of its applications. Today we will focus on the curl of the electrostatic field. We saw last time that it is zero. We will use that fact today to define a quantity known as the electrostatic potential. So let us get started. So we are still looking at electrostatics. The electric field is given by this integral, and again, that integral is, except for the very simplest of cases, not solvable. And so we need workarounds, and we saw last time one of them is Gauss's law, where we looked at the divergence of E. And we also saw that the curl of E is zero, but we didn't use that fact. What can we do with it? Well, saying the curl of E is zero means that E cannot be just any random field. It can, for instance, never be, no matter what configuration of charges I take, the electric field can never be y times x hat, simply because the curl of this field is not zero. And so, because it can't be just any field, we can use this to our advantage. We look at the fundamental theorem of calculus, which tells us that if we take some closed line, the line integral along this closed path of E dot dl, which is equal to the surface integral of the curl of E along any surface that has that line as its boundary. But because the curl of E is zero, that means that the closed line integral is zero. And following from that, we have that the line integral from a to b of E dot dl has to be independent of which path we take from a to b. Why is that so? Well, imagine that that were not the case, that going along one of those paths would give a different result than going along a different one. In that case, what we could do is go from a to b along one of them and come back from b to a along the other, and that closed line integral would not be zero. Those two paths would not cancel out. And so, because we know that this closed line integral has to be zero, the integral cannot depend on which of those paths we took. How can we use this fact now? We choose some reference point, which I called curly O, and some field point in space, which is characterized by the vector r. And we know now that the line integral from O to r is independent of which path we choose between those 2 points. Because of this, we can define a function v as this integral with a minus sign. The minus sign is simply there for historical reasons. It's a convention. Now, notice that the independence of this integral of the path is crucial for this definition to make sense. Because if it did depend on which path you took, then going from O to that point R along this path, for instance, would give us a different result than going along this second path. And as such, the integral itself would not be a function of R alone, but of R and which path we chose. So the fact that we have this independence means that this actually defines a well-defined function of R, at least once we fixed the reference point O. This function is known as the electrostatic potential, and let's see what we can do with it. Well, if we choose 2 points in space A and B, VB minus VA is equal to the difference of these two integrals, and if we switch the order of the boundaries on the second integral, we get the expression below it here. And finally, we use the fact that the integral from a to b of some function plus the integral from b to c of that same function is equal to the integral of a to c of that function. And so what we find is that VB minus VA, the difference in the potential between the points a and b, is negative the integral from a to b of E dot dl. Notice that there is no dependence on the reference point O anymore. Now, what we also know from one of the earlier lessons is that the difference of a function v between 2 points can be written as the integral of the gradient of that function. Remember, this was basically the fundamental theorem of calculus for gradients. But we now have two different expressions for VB minus VA, and therefore the right-hand sides of those two equalities need to be equal to each other. So the integral from a to b of the gradient of v dot dl and negative the integral from a to b of e dot dl have to be equal to each other. And that is true no matter which path we take between a and b, and no matter what the points a and b themselves are. The only way for this to be true is for the integrands to be equal to each other, and therefore e is equal to negative the gradient of v. This is what we were looking for. It turns out that because the curl of E is irrotational, has no curl, E can be written as the gradient of some function which is known as its potential. Now, I claimed this fact already in one of the earlier lessons, but I didn't prove it. The logic that I gave you here is actually a proof of this statement, at least in the context of electrostatics. Now, why would we care about the fact of being able to write E as the gradient of some scalar potential? Let's look at what the advantages are of doing this in this way. Remember from the very first lesson on electrostatics that the total force on a test charge due to multiple source charges is simply the vectorial sum of each of those individual forces exerted by each of the source charges on the test charge. Now we know that F is equal to Q times E, so if we divide in the principle of superposition the whole equation by the test charge Q, we get the principle of superposition for the electric field. Now we can go one step further. We just defined V as the integral up to a minus sign of E dot dl. So if we integrate both sides of the superposition for the electric field, so we integrate on the left-hand side E itself and on the right-hand side the sum of E1 and E2 and E3, etc., we find a principle of superposition for the scalar potential. But the advantage is that this is an actual sum because this is a scalar function. It's not a vectorial sum anymore. We're not adding arrows, we're actually just adding scalar functions now, which is a much easier thing to do. And so one aspect that is a huge advantage working with the scalar potential is the fact that when we have multiple charges, we need only calculate the potential of each of those charges separately and add them as such, not as vectors, not as arrows. An additional point is the electric field is a vectorial field. It has three components, Ex, Ey, and Ez. But we now know that E can be written as the gradient, again up to a minus sign, but the gradient of a scalar function, V. But that means that once I know V, I can just take this special kind of derivative, the gradient, and I get all three components Ex, Ey, and Ez, but V only has one component, it's a scalar function. So somehow, all the information that is contained in three functions, Ex, Ey, and Ez, is somehow summarized in one single function, V. How can that be? How can it be that Ex, Ey, and Ez, which are three functions, can be summarized in only one of them, one single function, namely V? And the answer is because Ex, Ey, and Ez are actually not independent of each other. The whole point of writing the curl of E is 0 means that the components of E have some dependence on each other. Specifically, saying that the curl of E is 0 means that each of those three equations has to hold. Partial derivatives of Ex, Ey, and Ez are related to each other through these relations. And because of that, it turns out that E can indeed be written, instead of looking at the information as three separate functions, Ex, Ey, Ez, that information can indeed be summarized in one single function, V. And so we only need one function, V, to be able to study the electric field. Once we know V, we take its gradient and we have the electric field. The units of the electrostatic potential are, well, the potential is defined as the integral of E dot dl. E has units of Newton per Coulomb, and dl is meters, and so V has units of Newton meters per Coulomb. Now Newton times meter is joules, so we have joules per Coulomb, and joules per Coulomb gets the name volt. So the unit of this electrostatic potential is volt. I also want to mention the role that the reference point plays in the definition of V. So we define V as negative the integral from some reference point O to a point R. But what if we had chosen a different point? So let's say I choose a point O prime and I define the potential using that point as a reference. I define that one as V prime. Well, notice that V prime, the integral from O prime to R with a minus sign in front of it, can be written as the integral from O prime to O plus the integral from O to R, both with minus signs in front of them. Now the integral from O prime to O is simply a constant. That means that if we know the potential with respect to one frame of reference, the value that it has with respect to another frame of reference would be the same V up to some constant. So all we're doing by changing the point of reference is to add or subtract a constant from the value of V all over space. Now, depending on the problem, we can make better or worse choices of which point to use as a reference. In many problems, and in the examples that I will show you on the next slides, we will do that as well. We take infinity to be that reference. So we take the points which are infinitely far away from the charges to be the point of reference. The only cases where we cannot do that is when the charge itself extends to infinity. So if we look at infinitely long lines, infinitely large sheets of charge, in those cases we cannot take the reference point at infinity because those integrals will diverge, and in those cases we will need to make a different choice, and we will look at them when we get there. But unless stated otherwise, I will always choose infinity as the reference. Now, what is the consequence of adding a constant to the value of V and getting V prime? Well, the answer is there is no physically noticeable, no physically meaningful difference between them. The difference between the potential at B and at A is the same, simply because whether we do it with a reference point O prime or O, the k's cancel out, the constant cancel out when we take the difference between them. Additionally, when we take the derivative of the potential, well, the derivative of k is 0. In other words, the gradient of V prime and the gradient of V are the same. And remember that the electric field is the gradient of V. The physically meaningful, physically measurable quantity is the electric field, and that one does not depend on the reference point we choose. So let us look at an example. We consider the same example we looked at in the previous lesson, namely that of a hollow spherical shell of radius capital R and uniform surface charge density sigma. Using Gauss's law, we found that its electric field was given by this expression here, depending on whether we are outside or inside the spherical shell. We want to use now what we saw on the previous slide to calculate the potential of this configuration of charges. The potential as a reference point, we choose infinity. And so what we need to do is calculate this integral. Remember, dl in spherical coordinates is given by this expression. And when we take the dot product of E and dl, we are left only with the dr term. And so the integral we actually need to calculate is this one, negative the integral from the reference point, which is infinity, to r, of 1 over 4 pi epsilon naught times q over r squared dr. The 1 over 4 pi epsilon naught and the q comes out of the integral. We're left with the integral of 1 over r squared dr, which is negative 1 over r. And that negative cancels the negative outside the integral, and we're left with this expression. And notice that the boundary term at infinity vanishes, and we're left with this expression. So this is the expression for the electric potential, the electrostatic potential, outside of the shell. What happens inside? Well, inside we need to calculate the same integral, but R sits now within the shell. And the way to calculate this is we calculate the integral from the reference point, so from infinity to the radius, plus the integral from the radius to whatever point within the shell we are sitting at. Now the second integral is 0 simply because the electric field is 0 within it. And so we are left with the integral of the same integrand, 1 over 4 pi epsilon naught times q over r squared, but now with boundaries infinity at the bottom, but capital R, so the radius of the shell at the top. Again, the term at infinity vanishes, and so we're left with this expression, but notice now, this is a constant. This does not depend on where we are within the shell. And so what we find is that as we move away from the spherical shell, as long as we're outside of it, the potential decreases linearly with the distance, but once we are inside it, it does not decrease anymore. It's a constant. Notice it is not 0. It is the choice of the reference point O, which tells us where it is 0. That fixes the point at which the potential is 0. It is not 0 within the boundary, despite the fact that the electric field is 0 there. And it makes sense because the electric field is the derivative, the gradient of the potential. The potential is a constant within the shell, and so if we take its derivative within the shell, we indeed get 0, but the potential itself is not 0. Don't make that mistake. We now want to look at what the equations of electrostatics look like in terms of the potential. So we know Gauss's law and the fact that the curl of E is 0, and that the electric field is equal to minus the gradient of V. But what do the divergence and the curl equations look like in terms of the potential V? Well, we know rho over epsilon naught is the divergence of E, and we can now plug in for E negative the gradient of V. And we find that rho over epsilon naught is equal to negative the divergence of the gradient of V, and the divergence of the gradient, we looked at this quantity already several lessons ago. We called it the Laplacian. And so what we find is that the Laplacian of V is equal to minus rho over epsilon naught. This equation is known as Poisson's equation. And if we now look at a special case, if we look at a region of space where there is no charge, so rho is 0, the right-hand side becomes 0, and we get that the Laplacian of V is 0. This is known as Laplace's equation. And in a couple of lessons, we will actually spend some time learning how to solve this equation. A lot of what we need to study in electrostatics can be done by studying these equations, and so we need techniques to solve them, and that will be our task in a couple of lessons. So this is what we find if we plug it into the equation with the divergence. What do we get if we plug it into the equation with the curl? Well, we know that the curl of E is 0, and if we plug in for E negative the gradient of V, we find the curl of negative the gradient of V. Now, we saw already several lessons ago that the curl of the gradient is always 0. In other words, we don't get an additional constraint on V by this equation. But this is not surprising. We actually already used the fact that the curl of E is 0 to define the potential in the first place. And so plugging it into this equation again does not give us anything new. Laplace's equation and Poisson's equation play an extremely important role, and as I mentioned, we will come back to them in several lessons. What we are trying to do is to find a way to start with the charge distribution rho in space and get the electric field. We know that the direct way, using an integral, is a bit too complicated, so we need a workaround, and that is why we introduced the potential in the first place. If we somehow are able to calculate the potential and then take its derivative, its gradient, we get E. How can we then relate V and rho? Well, we just saw Poisson's equation. So are we done yet? The answer is no, because Poisson's equation gives us the opposite of what we actually want. What we want to do is to start with rho and get v. Poisson's equation tells us that if we know v, we can take two derivatives, it's Laplacian, and that gives us rho. So what we need to do now is to somehow invert Poisson's equation, get v in terms of rho and not rho in terms of v. How do we do that? Well, just like we did with Gauss's law, we start with the simplest of cases, which is let's take a single source charge at the origin of some coordinate system, and we take the reference point for the definition of the potential at infinity, and the potential at some field point r is then this integral, which is the exact same integral we already solved 2 slides ago. Now, there's nothing special about the origin of the coordinate system. I could have chosen to put the source charge at some other point in space, and in that case, in the result of the integral, instead of regular r, we would have curly r, which is the vector going from the source to the field point, and we have the magnitude of that vector curly r here. Now we also have the principle of superposition for potentials, which means that if there are multiple source charges, we can simply add the potential created by each of those source charges separately. So if we have n source charges spread out in space somehow, the total potential at a point r will simply be the sum of those individual potentials. And if the source charges are a continuous distribution of charges, the sum becomes an integral and we get this expression. This is what we are looking for, but we can also make it more explicit by saying how those charges, how the source charges are distributed in space. Depending on whether they are distributed in 1, 2, or 3 dimensions, we would get one of these expressions here, which is very similar to the expressions we found for the electric field in terms of the charge distribution, with 2 differences. If you look at the expression for the electric field, notice that the curly r in the denominator has a square on top of it, so it's curly r squared. In the integrals for v, we have a single r there. That is a difference, but that is actually not the main one. The main one, the fundamental one, which makes the integral for the potential much easier to work with than the one of the electric field, is there is no curly r hat in the definition of v, which makes sense. V is not a vector. V is a scalar function. E is a vector, so that it has to be vectorial. And this curly r hat makes the integral of E extremely complicated because it changes direction for every point in the source charge. That curly r hat is not present anymore, which will make the integrals for v more doable. They can still be extremely complicated and we will still have to look at ways how to handle them, but it is an order of magnitude easier already. As an example of how to use the integrals we just saw, let's go back to the spherical shell we considered before. Now, I know we already solved this problem, but remember that we solved it starting from the electric field of that configuration which we got from Gauss's law. But the whole point is to be able to calculate it in cases when we don't have the electric field. So in that sense, using the electric field, if we already knew it, there was no point to calculate V in the first place. So I want to show you how to do it if we had not been given the electric field. So it will mostly be useful for cases where Gauss's law is too complicated to actually give us the electric field in the first place. But let us look at this example, and to be able to see what is happening, I will first make the sphere itself, the spherical shell, transparent, and I choose a coordinate system with its origin at the center of the sphere. Now we want the potential at some point in space, and I choose the orientation of my coordinate system such that the point in space where we're interested in is on the z-axis. So I choose this point here on the z-axis. That's where I want to know the potential, and the integral we saw is given by this expression here. So we need to calculate this. How do we do this? Well, what we do is we divide again the spherical shell into infinitesimally small pieces of surface, and dA prime, that small piece, has a magnitude of r squared sine theta d theta d phi. And notice the triangle from the origin to the field point we are interested in and to that part of the surface. And the angle created here at the bottom, I call it theta prime. Notice that the sides of this triangle, one of the sides, the one going from the origin to that piece of the surface, is the radius of the spherical shell r. The vertical one is z, the distance from the origin to the field point, and curly r is the line going from the surface from that part of the surface to the field point. And on this light blue triangle, we can use the law of cosines, which tells us that curly r squared is equal to capital R squared plus ZR squared minus twice capital R times Z times cosine of theta prime. We can plug this into the integral, both this and dA prime, and we get this expression here where, because we have a uniform surface charge density sigma, it can be taken out of the integral, and we get this expression, which is a double integral here. And the phi integral can be solved immediately because there is no phi dependence in the integrand, and we get a 2 pi outside. The 2 pi cancels, well, first of all, the pi in the denominator and the 4 in the denominator became a 2. And we're left with this integral over theta, where theta goes, as always, in spherical coordinates from 0 to pi if we have 1 over a whole sphere, over a whole spherical shell. So we need to solve this integral. This again is the integral we want to solve, and the way to solve it, or one way to solve it at least, is using a substitution. We define a new variable of integration t by this expression here, which is everything within the square root in the denominator, and consequently dt is equal to 2rz times the negative of sine theta prime, which cancels the negative that was there in front of it already. And plugging this into the expression we find, we get sine theta d theta, which is what we had in the initial integral above in the numerator, gives us dt divided by 2rz, and the 1 over 2rz comes out of the integral, and we're left with what you see here. And the boundaries of the integral, the boundaries of integration, when theta is 0, t is equal to r squared plus z squared minus 2rz, and when theta is pi, t is equal to r squared plus z squared plus 2rz, and so we're left with these two expressions here, and the integral of 1 over the square root of t is equal to 2 times the square root of t evaluated at the boundaries, and so we get the expression that I wrote here. Now we have to be careful here when actually calculating the square root of the square of r plus z or r minus z. Because what we get is not simply, for instance, the square root of r minus z squared is not simply r minus z, but it's the absolute value of r minus z. And that is equal to either r minus z or z minus r, depending on whether r is larger or smaller than z. So let us look at both cases. If we are outside of the spherical shell, z is larger than r, and consequently the square root of r minus z squared is actually equal to z minus r, which is what I wrote here. And the z's cancel out, we're left with a 2r in the brackets, which gives us this expression here. Now remember that the total charge of the spherical shell is q, which is the surface charge density times the surface of the shell, 4 pi times r squared. And if we plug this into the expression for v, we find that v is equal to this expression here, which is the exact same expression we found for the potential outside the spherical shell, starting from the result we found through Gauss's law a couple of slides ago. If we look inside the spherical shell, in that case, the square root of r minus z squared is r minus z, and we're left with this expression here. Now the capital R's cancel, and we're left with a 2z outside within the brackets, and it cancels the z in the denominator, and we're left with this expression. Once again, we can plug in q into this, and we find this expression, which again is a constant, and it's the same constant we found using the previous technique. This is how to use such integrals. So what have we seen actually about electrostatics? Well, there are three main players in electrostatics: the charge distribution rho, the electric field caused by that charge distribution, which we want to know, and the potential. Now, in a first step, we saw that if we have the charge distribution, we can get E by solving this integral, which in general is not solvable. And so we need a workaround. The way to do that was to introduce the potential V, and to go from rho to V, we got a simpler integral, one which does not involve curly r hat. Now, if we are able to solve this integral, we have V, and once we have it, we can take negative the gradient of V to get the electric field. So this is the logic of what we've seen until now. Each of these arrows can also be inverted. If you want to go from, instead of going from rho to E as we did here, if you want to go from E to rho, you use Gauss's law. If you want to go from V to rho, you use Poisson's equation. And going from E to V was the definition of the potential. V is equal to negative the integral of E dot dl. This gives us an overview of everything we know now about the relations between V, E, and rho, which are the main quantities of electrostatics. In the next lesson, we will look at how to use all of this to say something about electrostatic energy and work in the context of electrostatics. I will see you then.